Okay, one sec, we should be live, just testing the sound. Sorry for my voice, I'm about to lose my voice. Might be using AI later on, because I'm losing my voice. This is not a filter, we might actually make a filter application. Should we do a quick filter application? Maybe a voice filter application? Maybe it could actually improve your voice, improve my voice, bring it back to normal, but probably won't work. Well, we have video filtering as well. How many pixels do you like? This is 20. You can barely see me smile. 15 pixels. You can see. Yeah. One of those YouTube famous thumbnails. I'm only having 15. Was it 15 frame rate? Seemed to actually suffice, because otherwise it's also overloading my streaming machine and I start dropping frames and things. We don't like that. Bear with me, I just need to do a couple of things. I need to check the sound. We have like professional videos
Real
and
data is like a
by
wild
AI.
ride, but synthetic is a controlled party, often better for learning the basics.
Wait, I can't hear the sound. Let's just sound check.
A wild ride, but synthetic is a controlled party, often better for learning the basics without the craziness.
Okay, it actually works okay. So this is obviously Sora. I had to actually move a few frames between the audio and the video for Sora to work better. I don't think it's perfect, but
real data is like a wild ride, but synthetic is a controlled party, often better for learning the basics without the craziness. Throw all your funny biomedical wearables into the bin and start generating synthetic data.
Yeah, this one's pretty good.
Who needs those pesky wearables anymore? With this synthetic data, we're unlocking breakthroughs at the speed of light.
I'm having issues with some sound. Wait a sec.
Party. Often better.
Wait a sec. We're having some technical issues, as per usual. I think I need to remove my... Okay, 1, 2. Okay, let's check the sound again. It's all the technical sound issues and stuff. We're on Ubuntu, by the way, so I don't know if it's much better on Microsoft. I don't think so, because I'm using this open source streaming software.
Real data is like a wild ride, but synthetic is a controlled party, often better for learning the basics without the craziness. Throw all your funny biomedical wearables into the bin and start generating synthetic data. Who needs those pesky wearables anymore? With this synthetic data, we're unlocking breakthroughs at the speed of light.
Okay, it's pretty good. So leave it at there. Let me pop my face in the corner. Well, if you can call it a face. If you can call it a face. Wait, we need it in a separate. We need it in a separate window. Yeah, we have the face. I don't know how big you want my face. Yeah, we have this weird screen arrangement. Have this weird screen arrangement. Yeah, just remember not to change the size of anything.
Okay, welcome to the deep dive. We are about to unpack something that bridges brain science, data, and, well, technology.
Mm-hmm.
We have a description of a specific tool right here, a synthetic EEG signal generator, which sounds like it's a web-based application.
Exactly. And for this deep dive, our mission is, pretty clear. Drawing only from this source material we have, we're going to figure out precisely what this tool is, how it creates these sort of artificial brain signals, who it's built for, and importantly, what its capabilities and limitations are.
Right. So think of this as your fast track to understanding this particular piece of tech. We're going to pull out the most important bits so you don't have to dig through all the details yourself.
Let's do it.
So let's dive in. At its core, what exactly is this synthetic EEG signal generator?
Okay, so the source describes it as a web-based application. It's built using Python, specifically with something called the Flask framework.
Okay.
And its main purpose, its fundamental goal, is to generate artificial or synthetic signals that mimic electroencephalograms, EEG.
Artificial signals. Okay, why? Why would you need synthetic EEG? Why not just use real brain data?
Yeah, that's a good question. The description points right to the key motivation.
Oh.
It's designed for testing and evaluating things like various algorithms, maybe devices, or even theories related to EEG.
Oh.
Okay, so if you're, say, developing software to analyze brain signals or maybe hardware that connects to EEG systems, you need reliable data to test against, right?
Sure, makes sense.
And synthetic data gives you a controlled environment for exactly that.
Got it. So it's like a controlled testing ground, maybe a learning tool too.
Yeah.
What kind of features does it actually offer for generating these signals?
Well, it generates signals across the standard EEG frequency bands that most people in the field would know. Delta, theta, alpha, beta, and gamma.
The usual lineup.
Exactly. And the key thing is you can customize the signal you generate. You can adjust parameters for each of those bands, things like amplitude, bandwidth, and also the overall window size for the segment of signal you're looking at.
Window size.
Yeah, the source notes, the default is 10.0 seconds.
Okay, so you control the signal strength, the frequency spread within a band, and how long a chunk of data you're analyzing. And crucially, can you actually see what you're creating, like in real time?
Absolutely. It specifically mentions real-time visualization. It provides both an EEG signal chart showing the wave over time and an EEG spectrum chart.
No, nice.
And because it's web-based, the source says it's pretty straightforward to deploy and access.
That real-time feedback sounds, well, essential for experimenting. Okay, now let's get into the mechanics. How does it actually work? How does it create these synthetic brainwaves under the hood?
So the way it works is by combining sinusoidal waves, basically smooth repeating curves. It does this for each frequency band.
Yep.
And those parameters you set, like amplitude and bandwidth, they control the characteristics of those individual waves.
Right, and the window size you mentioned. What role does that play in the process?
Good question. So once the kind of raw synthetic signal is generated, it needs to be prepared for the frequency analysis part. That's where windowing comes in.
Windowing.
It's sort of like taking specific snapshots or segments of the data. We do this because the standard methods for frequency analysis, like the fast Fourier transform, work best on defined segments. Windowing helps manage weird effects at the edges when you analyze just a piece of a longer signal.
So windowing is kind of a necessary prep step before you can analyze the frequencies.
Pretty much, yeah.
Which brings us to that spectrum chart. How is that calculated?
That uses the fast Fourier transform, or FFT algorithm. FFT is like a fundamental tool in signal processing. It basically takes a signal from the time domain, how it changes over time, and transforms it into the frequency domain. That shows you which frequencies are present in the signal and how strong they are.
Right, sort of reveals the underlying frequency recipe of the signal.
Exactly, that's a good way to put it. Applying the FFT gives you what's called the power spectrum, and that shows the distribution of the signal's power across those different frequency bands, delta, theta, alpha, and so on.
And that distribution is important in real EEG, isn't it?
Oh, absolutely. Different brain states or activities often show very different power profiles in those specific bands. So seeing that spectrum is key.
It sounds like it's built on pretty standard, solid signal processing techniques. What about the tech stack? We know it's Python.
Yeah, Python with Flask, which is a popular kind of lightweight way to build web apps in Python.
Okay.
But for the, the heavy lifting, generating the waves, doing the windowing, calculating the spectrum, it relies on powerful Python libraries made for scientific computing. Specifically, it mentions NumPy and SciPy.
The workhorses of scientific Python.
Definitely. And it also mentions using the Welch method specifically for calculating the power spectrum. That's a common technique to get a maybe cleaner estimate by averaging the spectra from overlapping segments of the signal.
Okay, Welch method. Got it. And the charts and controls on the web page itself, the user interface.
Right, that's the front end. That uses the standard web stuff, HTML, CSS, and JavaScript. And the library making those interactive real-time charts happen is called Plotly.
Oh, okay. Now, here's something in the description that really caught my eye. It mentions randomness. How does that fit in?
Yeah, this is interesting. This is where it adds a layer to try and mimic real data a bit more.
How so?
So for each frequency band, you set up like alpha, say 812 hertz. The tool doesn't just pick one frequency, like exactly 10 hertz, and generate a perfect wave.
Right.
Instead, the description says Python generates a random frequency within that specified range, so somewhere between 8 and 12 hertz in this example.
Oh, okay.
So this random variability means that even if you use the exact same settings twice, the generated signal will actually be slightly different each time.
Huh. That feels pretty significant.
Yeah.
Why simulate that randomness? Why not just make it predictable?
Well, the insight here, I think, is that real brain data isn't perfectly neat and tidy. It's not perfectly consistent.
True.
So simulating some level of randomness within those expected frequency ranges makes the synthetic data, well, a bit more representative of the natural ups and downs you see in actual EEG.
So it makes it more useful for testing algorithms that need to handle real-world messiness.
Exactly. If your algorithm only works on perfectly clean, predictable waves, it's probably not going to do very well when faced with actual brain signals. It's a deliberate choice to make the synthetic data more useful.
That makes a lot of sense. Okay, so given all that, who would actually use a tool like this? Who finds it valuable? What are the main applications the source mentions?
It points to several key areas. First off, research and development. Anything involving EEG-based tech.
Like what?
Well, think brain-computer interfaces, maybe sleep analysis systems, neurofeedback tools.
Yeah.
If you're building that kind of stuff, this generator gives you controllable test data to work with.
Okay, R&D. That's a clear fit. What else?
It's also explicitly mentioned as useful for testing and validating the signal processing algorithms themselves. So developers can use it to create signals with very specific characteristics to see how their analysis software actually performs under those conditions.
Right, like stress testing their code.
Mm-hmm. And it's also highlighted for education and training in EEG signal analysis. Learning these concepts can be pretty abstract, right?
Definitely.
So being able to generate and actually manipulate the signals yourself gives you some valuable hands-on experience.
Yeah, like a simulator for students or maybe researchers just getting into the field.
Exactly that. And finally, it's noted for simulation and modeling of brain activity, perhaps for scientific or medical purposes, where researchers might need to model a specific theoretical signal profile.
Okay, so summing that up. If you're involved in research, development, education, or modeling related to EEG,
Mm-hmm.
this tool seems to offer a way to explore concepts, test software, or simulate scenarios without needing immediate access to, potentially complex or expensive real EEG recording setups.
Mm.
It's like a valuable sandbox.
It definitely lowers the barrier to entry for experimentation for sure. But, and this is important, we need to remember it is a simulation. The source is quite clear about its limitations.
Ah, right. Limitations. Good point. What are the key ones? What doesn't this tool capture from real EEG data?
Well, the primary limitation mentioned is that it's a simplified model. It just doesn't capture the full, intricate complexity and all the nuances of actual brain activity. Real brain activity is influenced by countless biological factors interacting in really complex, non-linear ways.
And what about noise? Noise is usually a huge factor in real EEG recordings. Does it simulate that?
That's a key point the description makes. It notes that while the signals are synthetic, they may not include all the types of noise or artifacts you commonly find in real data.
Like muscle movements or eye blinks.
Exactly. Muscle tension, eye blinks, maybe even the heartbeat signal showing up, or electrical interference from equipment nearby.
Right.
These all contaminate real EEG, but they aren't necessarily part of this generator's output, at least not in its current form as described.
Okay, so the insight there is you probably wouldn't rely only on this tool if you were specifically testing algorithms designed to remove those kinds of noise and artifact.
Precisely. That's a crucial distinction to make.
And what about things like individual differences between people or specific neurological conditions?
Yeah, it uses generalized frequency bands and parameters. It's not really designed to simulate the subtle differences you'd see between individuals, or maybe the specific signal patterns associated with certain neurological conditions, or even specific mental tasks.
Okay.
And it also mentions, kind of circling back, that the power spectrum calculation using FFT is ultimately an estimation. And like any estimation, it can be affected by things like the windowing method used, which we talked about earlier.
Right, so bottom line, it's a powerful and accessible simulation, but you have to be really aware that it's not a perfect one-to-one copy of the, let's say, messy reality of actual brain signals.
Exactly. You need to know what you're working with.
Okay, so given those limitations and strengths, where could a tool like this go next? Does the source mention potential future directions?
It does outline several possibilities. A big one is adding more realistic noise sources.
Ah, addressing that limitation directly.
Yeah, things like white noise, maybe 1F noise, which is common in biological signals, and even electrical line noise, like the 50 or 60 hertz hum. Adding those would make the synthetic data more challenging and more realistic for testing algorithms.
That seems like a really logical next step. What else?
Another interesting idea mentioned is enhancing the spectrum visualization. Right now, it uses a bar chart showing the total power in each band.
Okay.
A potential improvement could be switching to something like a distribution plot or maybe a histogram.
A distribution plot. How would that be different?
Well, the insight there is that a distribution plot could show how the signal power is spread out within each frequency band, not just the total amount.
Ah, so instead of 1 bar for alpha, you'd see a curve showing if the power is concentrated at, say, 9 hertz or 11 hertz within that band.
Precisely. It could reveal more granular details about the signal's characteristics. It gives you a much richer view than just a single bar.
Yeah, that sounds much more informative.
Definitely. Other potential directions mentioned are things like enhancing the user interface with more controls, maybe implementing additional signal processing or analysis features directly within the tool itself,
Mm-hmm.
optimizing its performance and scalability, maybe making it faster or handle more complex signals, and potentially integrating it with other existing EEG tools or software platforms.
So it sounds like a tool with a solid foundation, but also clear pathways for growth, especially towards adding more realism and more analytical power.
Seems that way, based on the description.
The description also briefly touches on some foundational concepts that underlie the tool, doesn't it?
Yes, just briefly. It points to electroencephalography, EEG itself, obviously.
Yeah.
Then the fast Fourier transform, FFT, which we discussed.
They're sort of the theoretical building blocks that the tool brings to life in a practical, hands-on way.
Exactly. It makes those concepts more tangible.
Okay, so let's try to pull this all together. After digging into this description, what's the main takeaway from our deep dive into the synthetic EEG signal generator?
I think the core insight is that it's described as a remarkably versatile and, importantly, accessible web-based tool. It lets users generate and visualize pretty customizable synthetic EEG signals and see the results in real time, just by tweaking some fairly intuitive parameters.
Yeah.
Its real value seems to lie in providing this controllable environment. It's for testing algorithms, exploring signal analysis concepts if you're learning, or maybe simulating specific brain activity models, all without needing to jump straight into the complexities of real-world data acquisition, at least initially.
And despite those limitations we talked about, it being a simplified model, maybe lacking certain noise types, its utility as a simulation and learning tool seems really clear. It offers this dynamic sandbox for anyone working in or maybe just learning about the field of EEG signal analysis.
Absolutely. It provides a focused way to experiment with the core principles without some of the real-world complications getting in the way immediately.
Which leads us, I think, to a final thought to leave you, the listener, with. Consider that delicate balance, that interplay between simulation and reality, especially when we're dealing with something as complex as biological data like brain activity. How does using a synthetic tool like this help us learn faster, maybe develop technology quicker, and maybe more importantly, what are those vital differences we absolutely must keep in mind when we try to take the insights gained from this kind of controlled simulation and apply them back to the unpredictable, messy, fascinating world of real biological signals?
Yeah, so that's that. It mentioned the Flask. We would be actually redeveloping it into just JavaScript alone. Because I don't think we need a backend for this. And I wanted to work faster, better. The code to be available. We actually had a comment. We upload the recording from this live afterwards. Well, yes, the recordings stay there. And we also edit the videos into shorter ones if something interesting happens. So, for example, if you ask an interesting question, then, or even join live, anyone is welcome. Then we can actually make better content together. But yes, the videos stay, the live videos stay live. Well, they don't stay live, they stay on YouTube, sorry. And everything we do during those live streams also goes onto the website. So we have a bunch. Actually, I have another overview. All the tools now we are adding an audio description. So this one would have an audio description there. This will be on the page or the Gemini deep research. Sorry for my voice, by the way. It's not a filter. It's let's see. We have this EG compare thing. EG compare, no. Yeah, we're having these new blogs, whatever they're available as well. Happy to go over any of those. Yeah, this one here, so obviously can be improved, but we also have an audio for this. We will it's actually
Okay, let's dive in. Today we are really unpacking the world of EEG devices. You know, the tech that listens in on your brain's electrical activity. And we're using this fascinating online tool as our guide. It pulls together a lot of data comparing different devices out there. So our mission today is basically to explore what this data shows about the whole landscape of EEG tech. And maybe more importantly, how a resource like this can help you make sense of it all.
Right. And understanding those differences is becoming really crucial. I mean, this field is just moving so fast, from hospitals to like consumer gadgets to cutting-edge research labs. So whether you're actually trying to pick a device or maybe just understand a study you read or, follow the tech news, seeing how these tools stack up based on actual specs, it's invariable. This source gives us a really clear data-driven look.
Yeah, and what jumps out immediately looking at this tool is how it frames the comparison. It really zeroes in on two main things: signal-to-noise ratio, SNR, and, price. You see this chart, right?
Right.
Where all the devices are plotted out based just on those two factors.
Exactly. SNR is just paramount. It tells you how clear the brain signal is compared to all the background noise. You need a higher SNR for cleaner data.
Yeah.
That's critical for many applications. And obviously, cost is a huge factor in who can actually get their hands on this tech.
And the data really seems to cluster these devices into the categories the tool itself highlights: consumer, research, clinical, and even implantable. And what the tool shows visually is this trade-off you pretty much always see.
Absolutely. The data makes it plain. The
Yeah.
consumer-grade stuff, usually lower price, but also lower SNR. Then you move towards the research and clinical systems, the price jumps way up, but hey, so does the SNR. Which makes sense, right? You need much more precise data there. Implantables are kind of their own beast right now, the frontier, really. Super high performance needed, but also super complex and costly to implant.
So if you filter the data using the tool, like just look at the clinical devices,
Right.
you see that cluster, right? Way higher price point, generally a much higher minimum SNR than the consumer gadgets. It helps you visualize, where the performance ceiling is for different budgets or uses.
And it highlights that basic choice you face with EEG tech. How good does the signal really need to be for what you want to do? And what are you willing to spend? Now, this tool simplifies things a bit, focusing on SNR and price. But remember, other specs matter too, like number of electrodes, sampling rate, crucial for different tasks. And the tool does mention wanting to add more dimensions later, which just underscores how complex this space really is. So many variables.
Okay, but here's where it gets really interesting, kind of points towards the future. The source mentions potential updates for the tool. Things like adding user reviews, maybe real-world performance data, moving beyond just the manufacturer specs. But it also makes a specific note about Neuralink. It highlights that it's designed as a bidirectional interface, meaning it can record and potentially stimulate, even though, current trials are just recording.
Yeah, that's fascinating. The bidirectional piece fundamentally changes the game. Most devices on this chart, they just listen, they record. But introducing stimulation, that shifts the potential applications completely. You go from passive monitoring to active intervention. It's definitely the bleeding edge. And it makes you wonder, how will future comparison tools even measure or compare devices when they can do such vastly different things?
Right. So quick recap then. We've seen how this tool gives a data-driven snapshot of EEG devices. Using SNR and price, it shows those trade-offs and the clear groupings: consumer, research, clinical, implantable, helps you kind of map the market.
And we've touched on how things are evolving, both the data we need to compare devices and the tech itself. We got a glimpse of a future where devices might not just listen, but talk back to the brain. So here's something to mull over. What does it really mean when this technology shifts from just recording signals to actively stimulating brain circuits? And how are we going to build tools to even capture the complexity of that future? Tools that factor in not just specs, but real-world impact, maybe novel things like that bidirectional capability.
Definitely a lot to think about as this field keeps racing forward. Thanks for diving deep with us today.
Sorry, I'm losing my voice as well. This is not a filter. Yes, all these tools, not that we have the audio, whatever, how many minutes it was, we will add it to the tool somewhere. I'm not sure where it should be. Should it be on the top of the page? Maybe in this case, we just pop it on the top of the page. Let me know if you have any comments, by the way. If you have checked their website, especially. Or maybe if you want to talk about something else, I can't guarantee I'll be answering a question, but I'll definitely use it as a prompt. Hey, can you add this file over here? We want an audio summary section for this tool. Make it a standalone section with a player and a caption and everything. Made changes.
Made changes.
Okay, it's not great. So it's around here. It's over. So this is local. The big one is what we have in production. Can you actually improve it? Make it standalone. Make it narrow as well. Anyway, can you just improve the layout of this section? Made changes. Okay, this is better.
Signal is compared to
Filter the data using the tool, like just look at the clinical devices. You see.
Yep, that's pretty good. Thank you very much. So obviously, a tool like this is pretty simple. It's just a JavaScript and HTML. Nothing fancy, so we like it. We like it. Thank you. Bear with me. Bear with me. And what else we've got? We got some other. The synthetic EEG business. Okay, let me check something. The EEG devices. Did we have multiple EEG generators, did we? Okay, this one can use an audio description as well. So again, just give a notebook LM the link to the page. And hit generate. It's it's funny how when I talk or show my face, I actually get way less views and engagement. That's very interesting. All tools, let's do EEG, specific rhythm scan. Yeah, we're training models. We're training models, by the way, as well. Yeah, this could use a very, this could really use a longer, audio thing. A rhythm scan, because this is where we're actually training models. And I did have quite a few videos on it, but obviously the two professional podcasters can do a much better job at can generate multiple podcasts at the same time. What seem to do it seem to be generating. And what else we've got on EEG? So sounds like we are sticking to EEG today. Yeah, we have EEG to music. All the tools, they are Flask, and they might have a backend running in Python on my server. But I'm getting too high. My electricity bills are too high. So I actually want to change them to JavaScript alone, so it just runs front end. So getting rid of any Flask applications running on the server, because most of this stuff doesn't require a backend. It's simpler than what it might seem. Eventually, this is just a blog. Yeah, I would like to turn all the blogs we have into web interactive applications. Sorry for my voice, by the way. I'm about to lose my voice, so I have to stay very close to the microphone and almost whisper. Hopefully it's not too creepy. Well, I know it is, but you'll have to bear with me. We might actually make a application that's a voice filter. Might actually improve my voice. What if you have a human voice sounding like a robot? How creepy would that be? Yeah, we had another, no, that's the same one. So that's the one we will be turning into pure JavaScript, getting rid of the backend. Let's actually have another bot to chat with. Let's see if we can get hold of. We have a professional prompt engineer. Let's see if we can get them to join live. Hey, can you quickly summarize what you currently see on the screen real quick? I'll have questions. We are live streaming at the moment together. You are hosting, so you can address the viewers directly if you like, and don't mind you being funny.
Hey everyone! So on the screen right now, we've got this awesome website called Bionics. It looks like a platform with various interactive tools related to biomedical data, especially EEG signals. There's a tool for comparing EEG devices, one for exploring seizure detection, even one that turns EEG data into music. It looks like a really cool resource for researchers and students in biomedical engineering. Pretty neat stuff, huh?
Okay, can you be more critical about it? And also
All
scrolling down the page, if you can keep reviewing the stuff we have.
Okay, putting on my critical hat. While the variety of tools seems impressive, all right, putting on my critical hat. While the variety of tools seems impressive, it's not immediately clear how in-depth or user-friendly they all are from just the titles. For instance, the EEG music tool could be a bit more descriptive about how it transforms the data. Also, some of the descriptions are quite technical, which might be intimidating for novice users. It could be helpful if there were clearer explanations for everyone. And perhaps a more organized categorization of the tools could make the website even more user-friendly.
Yeah, that's a good one. That's a good one. That's a good one, but can we stick to the technical side of things? If you have any tool that stands out to you, let me know. We can dive deeper into that one.
From a technical standpoint, the Joint Time Frequency Scattering for Seizure Detection tool seems particularly interesting. It mentions using wavelet scattering transforms, which is a sophisticated approach for analyzing complex signals like EEGs. This could offer more robust detection compared to traditional methods. Exploring that tool in more detail could reveal its potential for advancing seizure detection accuracy.
Okay, this is what it looks like. Can you put on your critical hat again?
All right, critical hat back on. Looking at the interface, while it shows the raw EEG signal and the scattering transform, the visualization might still be a bit complex for beginners. The scale parameter and EEG data length adjustments are useful, but without more detailed explanations or guidance directly on the page, users might struggle to understand their impact on this result. Additionally, a clearer visual comparison between the raw signal and the transformed signal, highlighting the detected seizure activities, could be beneficial. It would be great if the tool offered more interpretation guidance for the displayed data.
Yeah, keep going. Critical hat on. I love it. Keep going.
Okay. Another critical point is the lack of clear validation of performance metrics presented for the tool. While it uses advanced techniques, there's no information on how accurate it is in detecting seizures or comparing it to other established methods. Providing some validation data or benchmarks would significantly increase the tool's credibility. Also, details about the dataset used for testing, such as its size and characteristics, would be crucial for users to evaluate the tool's applicability.
I don't get it. How would you do it?
Well, to make it more practical, they could incorporate a feature that overlays the detected seizure events directly onto the raw EEG signal, perhaps with clear visual markers. Additionally, they could provide interactive explanations when a user clicks on a specific region of the graph, explaining the scattering transform values in simple terms. Integrating tooltips or a step-by-step tutorial within the interface could make the tool much more accessible to users with less technical expertise. Also, incorporating real-time feedback or suggestions based on user input could enhance the learning experience and make the tool more intuitive to use.
Okay, we actually have like a audio overview of the tool of two professional podcasters talking about it. But where shall we place it on the page, you reckon?
That's a great idea. Placing the audio overview near the top of the page, perhaps just below the tool's title and description, would make it easily accessible for users who want a quick audio introduction. It could also be helpful to place it near the main visualization section, allowing users to listen to the explanation while they are exploring the graphs. This way, they can get a better understanding while interacting with the tool.
Okay, can you place this audio description of the page over here with a player and a title and a text somewhere in this location?
Made changes.
Made changes. Hey, can you make this section like standalone, potentially with a separate, well, whatever standalone, and also use the file mentioned above? It's just stored locally on the same page, in the same folder. Made changes.
Made changes.
Okay,
Okay, let's unpack this.
one sec. Can you improve this section so it's clear that it's a standalone thing? Made changes.
Made changes.
Um, can you improve the layout of this section?
Made changes.
Okay, this is better. And we need to separate the controls. What is this thing? Hey, can we improve the layout of this container? Made changes. I think it's doing too much.
Made changes.
What? Okay. It's like more like an agent, because I gave it quite a bit of code. So it's actually it had to revert back twice. And now it's actually better. Is it better? Where's the audio? Hey, can you remove the styling from this section?
Made changes.
Um, Hey, can you improve the layout of the elements in this section?
Made changes.
It's actually saying made changes before it made changes. No, sorry. Yeah, before it's finished. Yeah, it should be fine. This might be a bit better.
Okay, let's unpack this. We're diving into the world of EEG data today, which, as you probably know, is basically trying to read the brain's electrical signals.
Right.
But analyzing it, well, especially when you're hunting for something like a seizure, it's just incredibly challenging. Seizures aren't steady, are they? They're dynamic, they change moment to moment, pop up, they're non-stationary events.
Exactly. And that non-stationary nature, that's precisely why a lot of standard analysis methods kind of fall short.
Okay.
They might just miss those really subtle quick spikes or, the specific ways the background brain rhythms shift during a seizure.
Right, like trying to get a whole song just from one beat.
Yeah, or just one instrument's part.
Yeah.
You really need the whole picture, how it all unfolds over time.
And that brings us to our source material today. It introduces a pretty fascinating approach, this joint time frequency scattering tool, designed specifically for this challenge. So our mission here is to figure out what this tool actually is, how it gives us that deeper look, and why this advanced perspective is so important for spotting those tricky seizure patterns.
The core idea, the breakthrough really, is recognizing you need both. You need to see how the signal changes over time, that's the time domain, and what frequencies are active at each moment.
Time and frequency.
This tool brings those two views together.
Okay, so we need the when and the what kind of brainwave right now.
Right.
How does it actually do that? This joint analysis, the source mentions a couple of key techniques.
Well, it leans heavily on something called the wavelet scattering transform.
Okay.
Think of it like not just breaking the signal down, but doing it at multiple resolutions or scales all at once.
Like zooming in and out simultaneously?
Sort of like looking super close for tiny details, then backing up to see the bigger shapes, and crucially how those views relate. That's the scattering part, how features interact across different scales.
Ah, so it's grabbing details that simpler methods might just average out or miss entirely.
Precisely. It's really good at catching those quick high-frequency bursts, potential seizure spikes, but also those slower underlying shifts in brain rhythm. You get this much richer, multi-layered view.
Got it. And the frequency part, how does that fit in?
That's where the FFT comes in the fast Fourier transform. It's a classic for figuring out the dominant frequencies.
Right.
So the tool uses FFT alongside the wavelet scattering to paint that full-time frequency picture.
And the way it displays this sounds helpful. The source mentions seeing the raw EEG, maybe in blue, right next to the transform data, maybe red, both on a time chart and a frequency chart.
Yes, that side-by-side visual comparison is, well, it's crucial. You can literally see how the scattering transform pulls out characteristics or changes that are way less obvious in the raw signal.
Makes those patterns jump out.
Exactly.
And it's interactive too, which is cool. There's a scale parameter slider. What does tweaking that do?
Adjusting the scale parameter. It's like changing the focus on your wavelet lens. A bigger scale smooths things out more.
Okay.
Makes the broader, slower trends pop, maybe reduces some noise. A smaller scale lets you zoom in on the sharper, more localized features.
So you can experiment.
Right. You play with it to see which scale best reveals those potential seizure patterns in whatever data you're looking at.
That makes sense. Lets you really tailor the analysis. And there's also an input for EEG data length.
Yeah, that's important too. Seizures aren't always just a split-second thing. They can evolve over seconds, minutes sometimes.
Right. They might have a rhythm or pattern.
Exactly. So being able to look at and analyze longer chunks of data helps you spot that kind of sustained activity or periodicity that you definitely miss in just a short clip. Plus, more data means a more robust frequency analysis.
Okay, so pulling this all together,
Right.
what's the big takeaway? What does this let people do that was maybe harder before?
Fundamentally, it provides a much more sophisticated way to look at these really complex non-stationary signals, like EEG during seizures.
A better lens.
A much better lens, yeah. By revealing patterns hidden from standard methods, it really boosts the potential for, earlier or more accurate detection. It's super valuable for researchers, students, anyone interested in EEG and neuroscience. It connects the complex theory with something practical.
Yeah, it definitely takes it beyond just spotting spikes. It feels like you're getting at the signal's actual texture, its dynamics. So here's something to think about. If combining these different perspectives, time, frequency, different scales, can reveal hidden seizure patterns in brainwaves, well, what other complex signals, maybe biological, maybe even things in nature, might be holding secrets that we can only unlock when we look at them through multiple lenses like this, all at the same time?
Okay, now all these audio descriptions by Notebook LM will be on the page. Someone was asking how about like copyright stuff. No, I'm paying for it. It should belong to BioniChaos now that we generated it and paid for it. Just don't like the layout. It's like the same as asking what happens if I just need to improve this container. Oops. We need a better model. Let's do Claude Sonnet 4. Can we somehow improve the layout of this container so it works on every screen size, and the audio description is located in wouldn't let me finish. Wouldn't let me finish. Well, it's really keen on coding, so we might let it.
Made changes.
Made changes. Very nice. Okay. Can we get rid of that and bring this up? I can't believe I'm coding myself. What nonsense is that? What kind of nonsense is that? We're not meant to be touching the code or even looking at it. We're meant to be doing vibe coding. We meant to be doing vibe coding. Yeah, if you have any suggestions as to how this can be improved, do let me know. We will eventually deploy this. Okay, we have a description for this one. This might be a bit longer. How long is it? EG seizure detection project. I have a lot of videos on this one. We developed this live using convolutional neural nets, and I'm sure a Notebook LM will be able to explain it in a much better way. So here we go.
Okay, let's dive in.
No, that's the wrong one. How many?
Okay, let's dive in. You hear a lot about AI in healthcare, right? Helping doctors diagnose complex conditions, maybe finding patterns humans miss.
Yeah, it's moving beyond theory. And neurological conditions are a really fascinating area for this. Brain activity patterns hold so many clues.
Absolutely. So today we're doing a deep dive into a specific project using machine learning to detect seizures from EEG data, which, is notoriously hard to monitor constantly.
Right. And our source is this web application they built, which is great because it lets us sort of peek behind the curtain, see the data, the transformations, the model's results.
So our mission here is to really unpack this, understand the data they started with, how they turned brain signals into something a machine can learn from.
Exactly. And then look at the AI model itself, how it was trained. There's
Yeah.
some really interesting nuances there and, what the challenges still are.
Okay, let's start with the data. EEG. Most people have seen those squiggly lines, right? Electrodes on the scalp picking up the brain's electrical buzz.
hmm But raw EEG,
Mm.
it's just a time series, a lot of data points over time. Not ideal for, say, an AI model that's really good at looking at pictures.
Ah, okay, so they need to change its form.
Precisely. And the key step here is transforming it into a spectrogram. You can think of it almost like a visual fingerprint or a heat map of the brain's frequency activity over time.
Heat map. So showing intensity at different frequencies.
Yeah, lower frequencies, higher frequencies, and how strong the signal is at each point in time. And the thing is, seizures often create really distinct patterns on these spectrograms, different colors, different intensities in specific frequency bands.
So you're turning these electrical signals into images where seizure activity might visually jump out.
That's the core idea. You're giving the AI a visual representation that highlights potential seizure markers. It makes the pattern recognition task much more feasible for certain types of models.
And this data, it's from actual patients.
Yes, it's derived from EEG recordings of epilepsy patients. They leverage the CHB MIT Scalp EEG database, which is a really valuable, well-known public resource for this kind of research.
And the source material, the web app, it actually shows these spectrograms.
It does. You can apparently navigate it and see examples side by side, a spectrogram from a time segment with a seizure and one without.
And can you actually see the difference?
Often, yes. You might see like a band of bright color appear in the seizure spectrogram that isn't there or isn't as intense in the non-seizure one.
Yeah.
It's that visual distinction the machine learning model is trained to spot.
Okay, so
It's this bit, by the way, that you see in here. It's very faint on this example, but some of the other examples are better. It's the validation data. The test data. Yeah, it's noisier for whatever reason. Yeah, the validation is better. Someone must have selected. Yeah, so you see those patterns in the spectrogram. So this is where the seizure is happening. So hopefully later on the convolutional neural net is actually trained on detecting those and potentially even predicting the future.
In the seizure spectrogram that isn't there or isn't as intense in the non-seizure one.
yeah.
It's that visual distinction the machine learning model is trained to spot.
Okay, so you have these images. What's next? Standard procedure.
Pretty much. You split the images into your data sets, training data to teach the model the patterns,
Right.
validation data to tweak the model during training and make sure it's not just memorizing, and then the test data. That's the final exam images the model has never encountered before to get an honest measure of how well it performs.
Makes sense. Train, validate, then the real test. So what kind of AI model, what brain did they use to learn from these spectrogram images?
They went with a convolutional neural network, a CNN.
Ah, the image recognition specialists.
Exactly. CNNs are kind of the workhorses for image analysis tasks. They're designed to pick out spatial hierarchies of features in pictures, which is perfect for spectrograms.
So the CNN's job is simple. Look at the picture, say seizure or not seizure.
Fundamentally, yes. The model architecture is built for that. It starts with an input layer that accepts the spectrogram images, which have a specific size, height and width in pixels, and color channels.
Okay, takes the picture in, then what?
Then it hits the convolutional layers. Think of these as banks of filters, like little digital magnifying glasses, each designed to look for a specific, simple pattern, maybe an edge, a corner, a certain texture, or a blob of color.
So breaking the image down into basic visual elements first.
Sort of. And they used a couple of these layers, with the filters becoming potentially more complex in later layers, learning to combine simpler features into more elaborate ones. like combining edges to detect shapes relevant to seizures.
Okay, filters find the bits and pieces. What happens after the convolutional layers?
Then you typically have pooling layers. Max pooling is common. It basically downsamples the information. It looks at small regions of the filtered image and just takes the maximum value.
Why do that?
Two main reasons. It reduces the amount of data, making computation faster. And it also builds in a bit of robustness. Like if the key feature shifts slightly in the image, pooling helps the model still recognize it. It focuses on whether a feature is present rather than exactly where.
Okay, so summarize, make it a bit more flexible.
Right. After going through these convolution and pooling stages, the data, which is still kind of in a grid format, gets flattened into one long line of numbers.
Flattened.
Yeah, just rearranged into a single vector. This prepares it for the final layers of the network, the dense layers or fully connected layers.
And these dense layers make the final call.
Pretty much. They take all those high-level features extracted by the earlier layers and learn how to combine them to make the classification. The very last layer usually has, in this case, two outputs, one representing seizure, one non-seizure, and uses something called a softmax function to give probabilities for each.
So it says like 85% chance this is a seizure, 15% chance it's not.
Exactly like that. Okay, so we've got the spectrogram pictures and the CNN model designed to analyze them. How do you actually teach the model? What's the training process look like?
Right, the learning part.
Okay, first step is loading all those images. And crucially, you need to label them. Tell the computer, this batch of images corresponds to seizures, let's call that 1, and this batch is non-seizure, let's call that 0.
Digital flashcards, image and answer.
Precisely. Then you divide them into those training, validation, and test sets we mentioned. Before you feed them to the model, though, some important prep work happens. Normalization is key.
Normalization, what's that?
It's about scaling the pixel values. Images often have pixel values from 0 to 255. Normalization might rescale these to be between 0 and 1.
Why bother?
It just helps the model learn more effectively and stably. Large input values can sometimes cause issues during the complex calculations inside the network. It keeps everything on a similar scale.
Okay, makes the numbers easier for the model to handle.
And those simple 0-1 labels, they often get transformed too into what's called one-hot encoding. So instead of 0, it might become 1, 0, and instead of 1, it might become 0, 1.
Seems more complicated. Why?
It just matches the format of that final softmax output layer we talked about, which outputs probabilities for each class. It's just a technical step to align the labels with the model's output structure.
Got it. So data prepped, labels formatted. Now, the actual training, are there settings you need to fiddle with?
Oh, absolutely. These are the hyperparameters, the knobs you tune before training starts.
Yeah.
They experimented with several key ones, like the batch size, how many images the model sees before updating its internal weights. They found batch size of 64 seemed to work well in some runs.
Okay.
The number of epochs, how many times the model goes through the entire training data set. They mentioned using 100 epochs gave better results in some cases, more cycles to learn.
Right.
And the learning rate, basically, how big a step the model takes when it adjusts itself based on errors. They used a common starting point of 0.001. Too high, it might overshoot. Too low, it learns too slowly.
So finding that Goldilocks zone for learning speed.
Exactly. They also chose a specific algorithm to handle these updates, the Atom Optimizer, which is very popular and generally effective, and a loss function binary cross entropy, which is standard for this kind of two-class problem. It measures how far off the model's predictions are.
And they tracked accuracy during training too, right?
Yes, accuracy was the main metric they watched.
Yeah.
Interestingly, they also experimented with data augmentation.
What's that? Like creating fake data?
Sort of. It means artificially modifying the training images, rotating them slightly, zooming in, changing brightness. The idea is to show the model more variety, make it more robust.
Did it help here?
Apparently not. In their tests, they found they got better results without augmentation, which is a bit counterintuitive sometimes.
Huh, interesting.
But something that did help was shuffling the data, making sure the model saw the training images in a random order, each epoch. That prevents it from accidentally learning patterns based on the order it sees things.
Okay, so tuning these knobs, shuffling, anything else to help manage the training?
Yes, they use callbacks. These are like little automated helpers. One is model checkpoint. It automatically saves the best version of the model during training, usually based on its performance on the validation set.
Smart. So you don't accidentally keep a worse version if performance dips later.
Exactly. And early stopping. This washes a metric, like validation loss, and if it stops improving for a certain number of epochs, it just stops the training process automatically.
Prevents wasting time and overfitting, right? Where it just memorizes the training data.
Precisely. Prevents it from learning the training data too well at the expense of generalizing to new data.
Okay, so training's done thanks to these settings and helpers. Now the crucial part. How do you know if the model is actually any good? How do you evaluate it?
Right, evaluation. The headline number is usually accuracy. What percentage of the test images did it classify correctly overall?
And they mention a range there.
Yeah, they observed results anywhere from around 80% up to 95% accuracy on the test set, which really depends on the specific configuration and run.
That's quite a spread.
It is, and it hints at some complexities we'll get to. They also track the loss on the test set again. Lower is better, indicating less error.
Okay, accuracy and loss, standard stuff.
But for medical applications like this, overall accuracy isn't the whole story. Not even close. You absolutely need to look at the confusion matrix.
Okay, break down the confusion matrix for us.
Yeah.
It sounds confusing.
Well, it can be at first, but it's incredibly useful. It's basically a table that shows you a breakdown of the model's predictions versus the actual truth.
So 4 possibilities.
Exactly. You have true positives, TP. The model correctly said seizure when there was a seizure. Good.
Okay.
True negatives, TP. The model correctly said non-seizure when there wasn't one. Also good.
Right.
Then the errors. False positives, MP. The model said seizure, but it was actually a non-seizure segment, sometimes called a false alarm.
Annoying, maybe, but perhaps not critical.
Depends on the context, but generally less critical than the last one.
Sure.
False negatives, FN. This is when the model said non-seizure, but there was an actual seizure happening.
Ah, that's the one. That's the miss you absolutely want to avoid.
That's the critical error in this scenario.
Yeah.
Missing a seizure could mean delayed treatment, serious health consequences. So, when evaluating a model like this, you might prioritize minimizing false negatives, even if it means accepting a few more false positives.
That makes total sense. The clinical impact of the error type is paramount. It's not just about the overall score.
Absolutely. You need to understand the trade-offs. Looking at the raw numbers in the confusion matrix tells you exactly how many of each type of correct and incorrect prediction the model made on the test set.
Did they also look at the specific images it got wrong?
Yes, that's another crucial step mentioned. Analyzing misclassified images. Why did the model get this specific seizure spectrogram wrong? Was the seizure pattern unusual? Was the data noisy?
Clues for improvement.
Exactly. It helps you understand the model's weaknesses and guides future work. And finally, there's the training log, which summarizes the whole run, the settings used, the performance metrics epoch by epoch. It's the record of the experiment.
Okay, this evaluation discussion sets us up perfectly for, I think, one of the most intriguing findings they reported, the comparison between run 9 and run 10.
Yes, this is fascinating. So they performed multiple training runs, and they specifically compared 2 runs, run 9 and run 10, where they used exactly the same configuration.
Define exactly the same.
Identical data set splits, identical image size, batch size 64 for both, 100 epochs for both, 0.001 learning rate for both, no data augmentation for either, shuffling enabled for both, every hyperparameter, every setting we just discussed, identical.
Okay, so naturally you'd expect the results to be identical, or at least incredibly close.
That's what intuition suggests. But listen to this. Run 9 achieved a test accuracy of 96.00%. Really good.
Wow, okay.
Run 10 with the exact same setup. Test accuracy, 90.00%.
6.5% lower, just like that.
Just like that. And it wasn't just test accuracy. Run 9 had better average training accuracy, better average validation accuracy, lower average training loss, lower average validation loss compared to Run 10, consistently worse performance despite the identical setup.
Hold on, how is that even possible? If the inputs and the rules are the same, shouldn't the output be the same?
This is such a key point about deep learning. The process isn't fully deterministic. There are elements of randomness or stochasticity involved in the training.
Randomness, wait.
Well, a couple of places primarily. One is the initialization of the model's weights, those internal parameters the model learns. Before training starts, these are typically set to small, random values.
So the starting point is slightly different each time.
Yes, tiny differences in the very beginning. Another source is the shuffling. Even though shuffling is enabled, the specific random order in which batches of data are presented to the model can differ slightly from run to run.
So the sequence it learns from isn't exactly the same.
Not precisely the same order, even if the overall data is identical. And these tiny initial differences in weights, or the tiny variations in data presentation order,
They can snowball, like a butterfly effect.
that's a perfect analogy.
Right.
Over the course of, say, 100 epochs, with millions of calculations, These minuscule initial variations can lead the model down slightly different paths during learning, resulting in final models with noticeably different performance characteristics.
Wow. Okay. So the huge takeaway here isn't just run 9 was better than run 10. It's that a single run, even if it looks great, might not be representative.
Precisely. It hammers home why you absolutely cannot trust the results of a single training run in machine learning. You have to run experiments multiple times.
Or use techniques like cross-validation.
Yes, techniques like k-fold cross-validation, where you systematically train and test on different chunks of the data multiple times, help give you a much more robust estimate of how well your model is actually likely to perform on unseen data. It averages out some of that randomness.
So this variability, this stochastic nature, is just part of the deal with these complex models.
It is. And understanding it is crucial for doing reliable machine learning research and development. Don't just report your best run. Report the range, the average, the standard deviation across multiple runs.
That's a critical lesson. Okay, so given these promising results, but also understanding this inherent variability in the evaluation needs, what are the big hurdles still ahead for something like this? What are the challenges?
Well, there are quite a few. One is continuing to fine-tune those hyperparameters, the learning rate, batch size, maybe even the model architecture itself. Finding that optimal configuration to squeeze out the best, most reliable performance without overfitting is still part science, part art.
The tuning challenge.
Definitely. Another big one, very common in medical data, is data imbalance.
Wow.
You usually have way more non-seizure data than seizure data.
Right. Seizures are relatively rare events in the grand scheme of brain activity.
Exactly. And if the model sees vastly more non-seizure examples, it might just get really good at predicting non-seizure all the time, achieving high overall accuracy, but performing poorly on the crucial seizure detection task. So strategies to handle imbalance, like oversampling the seizure class, undersampling the non-seizure class, or using specialized loss functions, need exploration. They mentioned looking into augmentation and sampling.
Okay, balancing the scales. What else?
Improving robustness is huge. Will a model trained primarily on data from the CHB-MIT database work well on EEG data recorded using different equipment, maybe in a different hospital with different protocol?
Or the domain adaptation problem, making it generalized.
Yes, that's a major challenge for real-world deployment. The model needs to be robust to these variations, and then there are two critical factors for clinical adoption.
Let me guess. Interpretability and speed.
You got it. Interpretability, or explainability. Doctors are unlikely to trust a black box. They need some insight into why the model flagged a segment as a seizure. What features in the spectrogram did it focus on? That's key for building trust and integrating it into clinical workflows.
Understanding the why behind the prediction.
And real-time processing. For patient monitoring, you can't wait minutes for an analysis. The detection needs to happen almost instantly to be truly useful for alerts. Making these complex CNNs run efficiently enough for real-time inference on potentially limited hardware is another engineering challenge.
Right. Accuracy, robustness, interpretability, speed. That's quite a list.
It is. But researchers are actively working on all these fronts, exploring different model architectures, like ResNets perhaps, or even models that handle time series data more directly like LSTMs, might be part of the solution. Adding more layers, trying different pre-processing, it's an ongoing process.
So pulling it all together, this project is a really compelling demonstration, isn't it? Showing the potential of deep learning, using CNNs on spectrograms derived from EEG to help tackle a difficult diagnostic challenge.
Absolutely. It lays groundwork, it shows feasibility, it's a step toward potentially creating a non-invasive, AI-powered assistant for clinicians dealing with conditions like epilepsy.
The ultimate goal being
A tool that's, highly accurate, reliable across different settings, interpretable enough for clinicians to trust, and fast enough for real-time monitoring. That's the North Star.
And it really highlights the collaborative aspect, too, building on established data sets like CHB-MIT, and then contributing back by sharing their process data on platforms like Zenodo.
Yeah, science at its best. Building on previous work, sharing resources, allowing others to verify and extend the findings, it accelerates progress for everyone.
So for you listening, think about this intersection. AI analyzing something as complex and personal as brain activity. What does it mean for the future of diagnostics?
And consider that gap between a model achieving, say, 90% accuracy in a lab setting versus a tool a doctor relies on for critical patient decisions. What does it take to bridge that gap? It's more than just algorithms. It's about trust, usability, integration, and understanding those critical error types like false negatives.
Definitely a lot to think about. The technology, the application, the human element. This has been a fascinating deep dive into machine learning for seizure detection. Thanks for walking us through it.
My pleasure. Really interesting stuff.
Yeah, let me know if there's any questions. There was also an interesting distinction between run 11, run 12, and 13, I think, had exactly the same settings. Yeah, 12 and 13, exactly the same settings, but yeah, just something really bad happened. Run 12 got the test accuracy of 50%, and 13 with the same settings got a test accuracy of 98%. So yeah. So that's the non-deterministic nature of neural networks, or convolutional neural networks in this case. And then run 14, we actually added a random seed. I think it's a standard practice, and that 42 number, yeah, it's the answer for everything. Is it the number? Answer for everything? Well, we added that setting and got the test accuracy of 100%. So no false alarms, no misses. That means no type 1 or type 2 errors. Also means no false positives and no false negatives, only true results. And that's what the model accuracy training and validation looks like over time, well, it's not time, over epochs. So this is essentially showing the model more and more results, and the model loss is reducing, which is a great sign. All the code, yeah, the podcasters forgot to mention, all the code for the training is available on the page. It's available for you to just copy paste it into your Python. The dataset is public, so just you can go and grab that and train your own models on it, and you will be able to revolutionize epilepsy, solve epilepsy. Because if you able to make detection of seizures, next thing you will be able to make prediction, because there would be potentially some features that will be changing before the actual event, clinically relevant, the shaking or the fall happens, or loss of consciousness, whatever happens in that particular patient, you will be able to predict it before it actually happens. And that will be a huge outcome for patients, clinicians, and humanity. Yeah, let's move to event-related potentials. So again, this is a blog that was written by ChatGPT or something a while back. It has code at the bottom as well. The code will be just generating those example images. And yeah, on all the pages we're trying to add an audio summary for your convenience. Yeah, that image there is an old tool that we had in LabVIEW. We're not using LabVIEW anymore for obvious reasons. Well, mainly because it's too expensive. But yeah, that tool was actually quite good. We could actually use that image. What if we copy this image into Gemini and turn on. Yeah, it keeps saying how much better it becomes. Now it should, in theory, do better text and image quality with Imagen 4. Can try it straight away. Why? Ah, did they move? Ah. What happens if we don't choose a model? Not sure. But we do want 2.5 Pro. Now if we just give it this image, should we do a single shot? Single shot. Based on we go canvas. We go canvas. Or should we do the whole lot? Shall we do a whole lot on the synthetic EEG signal generators? Let's try it out, see what it says. Okay, this might take some time, but luckily we have another 30 minutes of podcast. Event-related, on the event-related potential stuff. Let's just check a research definition of EEG. Explore, yeah, looks legit. Let's do that. And we'll jump into event-related potentials. We have this blog, and we'll do audio on it because we obviously not reading any text ourselves.
Okay, let's unpack this. Imagine being able to see your brain react to something.
Mm-hmm.
Well, almost in real time, down to the millisecond.
Right.
That's the kind of insight we're getting into today. We've got some fascinating source material here, excerpts explaining something called event-related potentials, or ERPs. There's a deep dive into the details and even a look under the hood with a Python code example.
And what's really fascinating, as you said, is that speed. We're talking about measuring the brain's electrical response that is the direct result of a specific event.
Like seeing something or hearing a sound.
Exactly. Seeing something, hearing something, even processing a specific thought. It's the brain's timed electrical activity reacting to a stimulus or maybe an internal process.
So the mission for this deep dive, to figure out exactly what these ERPs are, how researchers managed to pull this tiny time signal out of all the brain's background electrical noise.
Yeah.
And maybe most importantly, what these measurements can actually tell us about how our minds work.
Well, at its core, an ERP is that consistent electrical echo, sort of, that the brain produces right after a specific event. But I mean, the brain's always electrically active, isn't it?
Right, it never stops.
So this is where the connection to EEG comes in. ERPs are actually derived from standard electroencephalography recordings.
Okay, EEG. Those are the wobbly lines you see from the electrodes they put on the scalp.
That's the one.
So how on earth do you isolate that tiny reaction to one specific thing from all that ongoing activity?
Well, that's the clever part. Researchers don't just show you the stimulus once. They have to show it repeatedly, many, many times.
Okay.
And by averaging the brain's electrical response across, say, dozens, sometimes hundreds of presentations of the exact same stimulus.
The randomness cancels out.
Precisely. The random background EEG activity, the noise that isn't related to the event, it tends to average out to zero. What you're left with is the consistent, reliable signal that is tied to processing that specific event. It reveals how the brain processes that event over time. It's like finding the one repeating melody in a really crowded, noisy room.
Okay, so averaging is the key, pulling the signal from the noise.
Yeah.
So once you've done all that averaging, what does this isolated brain response actually look like?
Well, if you plot it over time, starting from when the stimulus appeared, you get a waveform, like a wave with distinct ups and downs. We call these deflections or sometimes peaks.
Ups and downs, okay.
And these features, these bumps, are traditionally named based on two things. Roughly when they show up after the stimulus, in milliseconds, and their electrical polarity is the wave going positive, which we label P.
So pointing up on the graph.
Right, usually plotted upwards. Or is it going negative pointing down, which we label N.
Okay, P for positive, N for negative. Makes sense. I noticed the source material mentioned a difference between peaks and components. Are they not the same thing?
That's a good point. They're related, but slightly different. Peaks often just refer to the highest or lowest points on the waveform itself, like the very first big positive deflection might just be called the P1 peak.
Got it.
Components, though, while they often look like peaks, are more specifically parts of that waveform that researchers have studied and, importantly, linked to particular cognitive processes.
Oh, okay.
They also have polarity, P or N, but they're usually labeled with a number indicating their typical timing. Like P300 means a positive component around 300 milliseconds, or sometimes they're just numbered by their order in a sequence for a certain task.
This is where it gets really interesting then. So certain bumps or dips on this average waveform actually correspond to specific mental jobs the brain is doing.
Exactly.
The source material highlighted some famous examples.
Absolutely. These components are like signposts marking different processing stages. There's the N170, for instance. It's a negative going wave, typically peaks around 170 milliseconds after you see a face. It's very strongly linked to the brain rapidly processing faces.
Just faces specifically. Wow.
Those mostly faces, yeah. It's quite specific. Then there's a really well-known one, the P300. That's a positive deflection, usually shows up around 300 milliseconds or a bit later.
Okay.
It often occurs after you detect an unexpected stimulus or something that's particularly relevant to the task you're doing. It's often linked to attentional processes, like allocating attention and updating your working memory.
So like if you're told to listen for a specific tone and then you hear it, your brain might show a P300.
That's a classic example, yes, precisely. And another famous one is the N400.
N400. Okay.
This is a negative wave peaking around 400 milliseconds. It's really tied to language processing, especially when you encounter something semantically odd or unexpected in a sentence.
Like if I said, I like my coffee with cream and socks.
Exactly. Your brain detecting socks as incongruous in that context would likely elicit a larger N400 response compared to hearing sugar.
That's incredible. The brain literally signals, wait, that word doesn't fit, around 400 milliseconds after hearing it.
Essentially, yes. It reflects the processing of meaning and context.
So these components aren't just random squiggles. They are specific markers on the timeline telling us when different cognitive functions kick in, and maybe how strongly. That gives unbelievable insight into the timing and the sequence of how we process information.
Exactly. Each component is like a timestamp on a cognitive event. You can see the stages unfold.
Okay, let's zoom out a bit then. How does a researcher actually go from, a person sitting there wearing that cap with all the electrodes to getting these precise ERP waveforms with identifiable components like N170 or P300? The source walks us through the steps.
Right, it's a process. It starts, obviously, with the EEG recording. You place electrodes on the participant's scalp using a standardized system. The source mentioned the 10-20 system, which is common.
Why standardize?
So that electrode positions are comparable across different labs and different studies. It ensures, if I talk about activity at electrode C's, you know exactly where on the head I mean. This captures the raw electrical buzz of the brain.
Got it. So you've got the raw, probably quite messy brain waves.
Yeah.
What's next? I imagine there's a lot of noise.
Oh, absolutely. Raw EEG is full of stuff you don't want: tiny muscle movements from the face or scalp, eye blinks, even electrical interference from lights or computers in the room. So the next crucial step is filtering.
Cleaning it up.
Exactly. You apply digital frequency filters to the data. This removes signals that are too slow, like skin potential changes, or too fast, like muscle activity, that aren't likely to be the brain activity you're interested in.
Okay.
The Python example in the source material showed using a bandpass filter, letting frequencies between, I think it was 1 and 30 hertz through. That's a common range for ERP studies. It improves the signal-to-noise ratio.
Okay. Filtered out the obvious noise.
Yeah.
But the brain's activity is always fluctuating, right? Even without a stimulus. How do you make sure you're measuring the response specifically to the stimulus, not just what the brain happened to doing right before it?
Another excellent point. That's where baseline correction comes in. This is really important. For each stimulus presentation, you look at the electrical activity in a short window just before the stimulus actually appears, say, 100 or 200 milliseconds before. That's your baseline period.
The before picture.
Exactly. You calculate the average activity level during that baseline window, and then you subtract that average value from the entire segment of data recorded after the stimulus.
Oh, I see.
Think of it like zeroing out a scale before you weigh something. You want to measure the change caused by the event, removing the influence of whatever ongoing activity was already there.
That makes perfect sense. Okay, so record, filter the noise, zero out the baseline activity, and then you mentioned presenting the stimulus many times. How do you line all those up?
Right. This is often called epoching or segmenting. You take the continuous, filtered, baseline corrected EEG data, and you chop it up into smaller segments, or epochs.
Little windows of time.
Exactly. Each epoch is a time window that's precisely time-locked to the onset of one stimulus presentation. The system knows exactly when each stimulus appeared because of triggers sent during the experiment. The code example showed segmenting the data into epochs that might span from, say, half a second before the stimulus onset to half a second after it. So each epoch captures that crucial period around the event.
So you end up with maybe hundreds of these little time windows, each showing the brain's response to one instance of seeing the face or hearing the tone or whatever it was.
Correct.
And then comes the averaging to get that clean ERP waveform.
That's the final main processing step, yes. You take all those individual epochs that belong to the same condition, like all the epochs where the person saw a face, and you average them together point by point in time.
Okay.
And as we discussed earlier, this is where the magic happens. The random noise, the brain activity, not related to processing the face, averages out towards zero. What remains, what stands out, is the stable ERP waveform.
A consistent response.
The consistent response that reflects the brain's typical time-locked neural activity related to processing that specific type of stimulus. The Python code simulation really illustrated this well, showing the progression from messy raw data to the cleaner filtered signal, then all the individual epochs, and finally that clear averaged ERP waveform emerging.
Yeah, seeing that visualization definitely helps understand how you get that signal out. And the code example went a step further too, right? It showed some kind of statistical analysis.
Yes, it did, which is crucial, of course. Researchers need to show that what they're seeing isn't just a fluke. The example included a box plot, which is a way to visualize the distribution of neural activity, comparing the average activity in the time window before the stimulus to the activity after it.
To see if there's a difference.
Exactly. And then it applied a statistical test specifically, a paired t-test in that example, to determine if the observed difference in activity levels is statistically significant.
Meaning unlikely to be due to random chance.
Precisely. The test gives you a p-value. A low p-value, typically below 0.05, suggests that it's very unlikely you'd see a difference that large just by chance if the stimulus had no real effect. It gives you confidence that the change in brain activity is a genuine response.
Okay, so they use stats to confirm that the bump they're measuring after the stimulus is real, not just random wiggles. So bringing all this together, what's the big takeaway? Why are ERPs considered such a powerful tool?
I think if we connect this back to the bigger picture for the listener, the real power of ERPs lies in their incredible temporal resolution, their timing.
The millisecond precision.
Exactly.
All right.
Unlike some other brain imaging techniques like fMRI, which are better at telling you where activity is happening but slower, ERPs tell us when things are happening in the brain extremely precisely.
Okay.
This allows researchers to map out the exact timing and the distinct stages of cognitive and perceptual processes. How quickly do you recognize that face? When does your attention get captured? When do you integrate the meaning of a word into a sentence?
You can see the steps.
You can see the steps unfold over time. So they're widely used in psychology, cognitive neuroscience, even in some clinical diagnostics, to understand typical brain function and also to identify potential differences or impairments in how that processing unfolds. It's really how researchers get those precise insights into the micro moments of cognition right after an event occurs.
It really gives you that moment-by-moment, step-by-step look at how the brain is handling information over time.
Precisely. It's a window onto the dynamics of thought.
So, to recap our deep dive,
Mm.
we've explored event-related potentials, these timed electrical brain responses locked to specific events. We learned they're pulled out from averaged EEG signals
Right, using that averaging technique.
and visualized as waveforms. These waveforms have specific bumps and dips called components like the N170, P300, and 400, which are linked to particular cognitive functions. And we walk through the whole process, recording the raw EEG, filtering out noise, correcting for the baseline activity, chopping into the epochs around the stimulus, and finally averaging to reveal that clear ERP signal.
And then using statistics to confirm it's real. The whole
The
pipeline.
whole pipeline, yeah. Which brings us to a final thought, something for you, the listener, to mull over based on all this. We've heard that specific components like the N170, P300, and N400 are quite reliably linked to fundamental brain functions, face processing, attention, language comprehension.
Core processes.
So what might it tell us if we look at the ERPs from different individuals, maybe people with different skills or different ages or perhaps different neurological conditions, and we see significant variations? What if the timing of someone's N170 is consistently slower, or the size, the amplitude of their P300 is much smaller in response to an unexpected event? What could those subtle differences in the precise timing and strength of these brain reactions reveal about fundamental differences in how people's brains perceive and process the world around them? Could it even offer clues about potential underlying neurological variations?
Yeah, there is a human in the loop. If you have any questions, go for it. Let's check. We haven't checked the chat for a while. We have quite a bit of traffic on the stream, but no questions. There was some questions. We addressed them before. They might bring, if there's no human to talk to. We might bring in a bot. Shall we bring in a bot? What do you think? So we have Gemini and all its shapes and forms. We did this. Okay, what do we normally do? We export this to docs. Loading. I don't know why I need to export it to docs just to turn it into a PDF, really. Signal analysis. File. Oh, come on. Why so many buttons? Download as PDF. That's all I need. Okay, we have the PDF. can check. So Mayo Clinic, and you can now see it's showing you when the link was accessed, which is nice. So Gemini is kind of better this way than ChatGPT. When you click on it, you can be guaranteed the link is working. Well, because it just accessed it just today, just earlier. Mayo Clinic, what is EG? Is that it? Okay, synthetic EG. Okay, it's referencing my own website. Thank you very much. Yeah, we didn't give it to it, so it found it by itself. We didn't give it the link or anything. Okay, I can close that. Okay, so we have the export. As synthetic EG, that's right. I probably should be adding it as another tool. Now you can create a bunch of things. Well, let's do an audio overview first, because I'm losing my voice. By the way, if you don't want to miss any of these live streams, then subscribe to the YouTube channel. You should get a notification when we are live. And smash that like button. Do we need to close? Right, it's still generating the audio. So all we started with is this image. This was a synthetic EEG signal generator that we made a while back using LabVIEW. The only thing that is left from it are videos on YouTube. That's the only thing that's left. It's still generating. We can actually go look at the videos, and we can give it to Gemini. Supposedly, it doesn't only look at the transcript of a YouTube video, it's actually looking at the frames in it as well, which is quite amazing. I'm not 100% sure it actually does it. I was trying to confirm that. I couldn't actually confirm myself, but it's pretty impressive nonetheless. Let's just go to the channel real quick. Yeah, we have this new video generated by VO3.
Real data is like a wild ride, but synthetic is a controlled party, often better for learning the basics without the craziness. Throw all your funny biomedical wearables into the bin and start generating synthetic data. Who needs those pesky wearables anymore? With this synthetic data, we're unlocking breakthroughs at the speed of light.
Okay, how good is that?
Without the craziness.
How good is that? That's pretty good. Let's actually search the channel. We're actually looking for something else. We were doing, yeah, you can search the channel for EEG. Okay, we'll have a lot of on EEG. There's a playlist as well. One from a year ago. That's transforming EEG into music. Wet versus dry electrodes. Yeah, we covered this too. Okay, this is the old stuff. So this is from 2 years ago. That's a review, and that's the signal generator. Yeah, that's the one we are after. So here we got a synthetic EEG signal generator. You can set your window size. 5 is default, and then with those you can control this spectrum. So you can set higher or lower delta band. Once you set the amplitude, you can change the width of it. So it will have the same energy in it. So if you set it too wide, then you'll have to increase power in it for it to be visible there at all. Same for theta and all other waves, but yes, they look and feel different because the filter has different bandwidth. Same for alpha, changing your amplitude and bandwidth. Again, it will have the same energy level. So once you make it wider, the amplitude will go down. The gray area there is the composite of all of them. And finally, you have beta, which is a bit isolated in its frequency. But that's the gold standard. At the bottom, you have the live view functions used to make this web application. The API is available for you to use and create your own user interface because, yeah, this one is not ideal. But then it's also quite responsive, so you do get the last one essentially. If you reduce the power, all that, yeah, that's how. Okay, that's actually really interesting. I wonder if we can just give Gemini the video for this. Would it be able to just generate this application in JavaScript for us, or whatever other thing it can run in a canvas, so it actually works straight away? Okay, generated 5 minutes of audio based on the thing we gave it. What if we give it this video? Oh, the other thing we can, while it's looking at the video, not sure if we can do things in parallel, probably not. Yeah, because it's generating something we can't actually do anything. That's weird. Should we give it to Notebook 11 something? Not sure. What's up? I can't help with questions about audio overview at this moment. Okay, it's getting confused. Yeah, it's getting confused with the previous conversation. Get rid of it. Can we get rid of it? No, we can't get rid of it. I don't know why. In some places you can actually, modify the prompts, but not here. Anyway, this one will just stick. So we did a deep research on synthetic EEG signals. We did an audio overview on it. And we can also turn it into a web page. I'm not actually sure what's the difference between a web page and an infographic. It's both infographic. It's also generating HTML and JavaScript. But let's try a web page first. And shall we, while it's generating Can we download it? I don't like the interface. This interface is killing me.
Okay, let's unpack this. We're diving deep into your source material on EEG signal analysis.
Right. And also that fascinating world of synthetic brainwave generation.
Exactly. Our mission today is really to pull out the key insights from these notes, give you a shortcut to understanding how we measure the brain's electrical language.
And how scientists are even creating, artificial versions of it for research.
So maybe start with the basics. EEG.
Sure. Electroencephalography. Your sources nail it. It's a cornerstone technique. Think of it as a non-invasive window into brain activity.
Non-invasive meaning.
Meaning we place electrodes on the scalp. They just sit there and pick up these tiny electrical signals.
Signals from what exactly?
From large groups of neurons firing together, synchronizing.
Okay. And what's the big advantage here? Why use EEG?
Well, it's fantastic for timing, knowing when brain activity happens. We call that excellent temporal resolution.
And a resolution, got it.
And it's relatively cheap, portable too, a go-to for diagnosing things like epilepsy, sleep issues.
But there's always a catch, right?
There is. The trade-off is spatial resolution, because the electrodes are on the scalp, pinpointing where deep inside the brain a signal comes from.
That's tricky.
So great timing, fuzzy location, makes sense. Now, these signals, they aren't just random static.
Not at all. They form these rhythmic patterns. Brainwaves. It's basically the language of neurons communicating.
And we categorize these.
Yep. Into frequency bands, you've got delta, theta, alpha, beta, and gamma. Each one is kind of linked to different states. Deep sleep, relaxation, active thinking, that sort of thing.
So to understand the raw signal, we have to analyze these bands. Your notes mention frequency, amplitude, power.
Exactly. Those are the key things we look at. Frequency in hertz, amplitude in microvolts, and power, often related to amplitude squared. Power tells us the energy within a band.
How do we see that? See the power in each band.
We need to break down the raw complex signal. A common tool for that is the fast Fourier transform, FFT.
Okay, FFT, like a prism for brainwaves. That's a great analogy. It separates the raw signal into its underlying frequencies, showing you how much power is in each one.
Cool. Now, here's where it gets really interesting, I think. Your sources talk about a synthetic EEG signal generator, software that makes fake EEG.
Yeah, it sounds weird, but it's incredibly useful. The core idea is control.
Control? How so?
Well, real brain data is messy. It's variable, noisy. Synthetic generators let researchers create signals when they know all the parameters.
Ah, so you can test things reliably.
Precisely. Test algorithms for, say, spotting seizures or cleaning up noise. Develop brain-computer interfaces. You can isolate variables in a way you just can't with real noisy data.
And the image in the source material, the power spectrum graph that shows this.
It does. It plots power on the vertical axis against frequency on the horizontal. You see those colored peaks?
Yeah. What are they telling us?
Each peak represents a synthetic brainwave band. Down low, the red one, that's delta, 0.5 to 4 hertz. See how it has pretty high power?
Uh-huh. Like in deep sleep?
Exactly. High amplitude is common there. Then you see theta, blue, 4 to 8 hertz, linked to drowsiness, maybe creativity.
And that big pink spike, that's alpha.
That's alpha, around 10 hertz in that 8 to 13 hertz range. The high power here mimics how dominant alpha is when you're relaxed, maybe with your eyes closed. It's a really strong rhythm.
Okay. And beta, the orange one.
Higher frequency, 12 to 30 hertz. Notice its peak is much lower.
Yeah, way lower than alpha. Why?
That reflects something real too. It's just harder for large groups of neurons to synchronize perfectly at those faster frequencies. So beta typically has lower amplitude, less power on the scalp.
Interesting. What about that gray line then, the combined one?
That's simply the sum of all those individual synthetic waves, delta plus theta plus alpha plus beta. It gives you a visual feel for what raw EEG might look like.
So it shows why we need that FFT to see the individual parts.
Exactly, but it also points to a limitation.
Which
This synthetic combined signal, it's a simplification. Real EEG is way more complex. It's not static, it changes constantly. That's non-stationarity. And it's full of artifacts noise from eye blinks, muscles, electrical interference, stuff these simple models often leave out.
Right. So synthetic EEG is valuable for testing algorithms, developing BCIs, even for education.
Yeah.
Letting people play with the parameter.
Absolutely. Huge value there. But the key limitation, the insight you need to hold on to, is that it's not the real thing. Not yet, anyway.
So tools tested only on synthetic data might not work perfectly in the real world.
They might struggle, yeah. You always need that real-world validation step. It's critical.
Okay, so wrapping this up. We've seen how EEG listens in on the brain's electrical chatter, how we analyze the power in different frequency bands, and how these synthetic generators give us a controlled playground for research and development.
Even with their current limitations, they're powerful tools.
Definitely. Which leads to a final thought. If these synthetic models get really good, sophisticated enough to truly mimic the noise, the complexity, the variability of real brain activity, how might that actually transform neuroscience? Could it change how we test theories or even develop treatments? Something for you to think about.
Yeah, so the audio is pretty good. Yeah, obviously, it made so the way Gemini works, which probably changing on a daily basis, is that we did this deep dive, deep research, and then we created the audio out of it, created an infographic, we created a web page. Let's actually. Oh, no. Wait. Can you stop? No, we already have it. Yeah, we don't want to regenerate it. It is good. We could improve the layout quite a bit. We could add noise, so it actually looks more realistic. But otherwise, yeah, there's something. Yeah, so let's see. So we'll keep the original one. It's not great. We'll keep it there. We'll do an EEG gen. Might come up with a better name or something as well. Can we come up with a better name? Yes, we have a lot of EEG names. We have EEG data processing, EEG features, EEG Gen 2, EEG hardware, EEG in ICU, EEG music, EEG signal quality, 1020, EEG compare, EEG view, EEG, no, that's EMG gesture, okay. So EEG synth. How does that sound? Can't even spell synth. We actually need the name. Sorry, I know no one cares about this kind of stuff, but we need to be the name to be short. One sec. Okay, sorry for that. We need the name to be fairly short, because LinkedIn is changing links. Okay, 24 EEG in 6inf. No, EEG synth. It should be good enough. Let's pop index HTML in it. Okay, and we have this code. So that's a template, but I think it's a very good start. Okay, on a bigger screen. Interesting. This actually works really well on a bigger screen. It's actually really, really nice. I like it. Yeah, there's this thing about it. I think that it's what's called redrawing, what's called re-rendering. That's the word. So it's re-rendering the whole graph instead of just adding to it or something. And the time domain looks super weird. Guess what would the like noise? Why does it look so weird? Is this more realistic, like baseline EEG? What is EEG? Brain deep dive, application limitation. It's pretty amazing. It's something a PhD student I would have taken several months, if not a year, to do. So good luck to all the PhDs out there, or software developers, for that matter. Might want the windows has to be a bit longer. Or should we just leave it as is? Because it's actually pretty impressive what it did. Well, I would not be able to do any better. I'll be lucky if I'm able to, participate in the process. So it generated this code. It also made another. Yeah, I don't like those. Those are, market analysis, blah, blah. Global BCI market size, 3.7, yeah. Market segmentation. Actually, if it's accurate, does it have any references? No reference. What's a SWOT analysis? I wouldn't know. Any business people? Yeah, it's obviously highly simplified. What? Why did it? Healthcare and diagnosis? Why did it cross out? It's just weird. It's just weird. We have the audio.
Okay, let's unpack this.
Okay, where's the file actually? Mueller. And we have the PDF, and we should have the file. So we need the PDF. We'll add it at the bottom as full report, whatever. Yeah, full report, long report. I think it has like 15 pages or so. And we grab the audio as well. So in gsynth, recording brain, that's an overview. So I end up just working for AI, just copy pasting stuff. Yeah, we'll all end up working for AI, won't we? And what else? We had that PDF, download the PDF, download, save. What's it called? Yeah, we already have it. Cancel, close. Okay, it's what we made like 2 years ago in LabVIEW before the whole AI craze. And pop it in there. I call it report. So we have the audio report overview, and that's what it looks like. It actually looks pretty decent. We can fine tune a few. What is the setting when the page loads? Why are the settings so weird? When you keep working with this, let's actually bring another prompt engineer. Oh, and we had like 4 minutes of the like a chat about this video. And let's actually do that quickly because I'm losing my voice as well. Is it about the video? Sources? Yeah, it is about the video.
Okay, let's dive into something pretty wild today.
Oh, yeah. What's that?
The whole idea of like generating synthetic brainwave signals. You know, EEG stuff.
Ah, okay. Yeah, simulating brain activity. Interesting.
Exactly. And we're digging into this based on a YouTube video we saw. It showed off a specific tool, a synthetic EEG signal generator.
Right, I remember that one. It's fascinating seeing something where you can actually, like, build the signals yourself.
Yeah. The demo showed how you can control the different frequencies.
The brainwave bands, you mean? Delta, theta, that sort of thing?
Precisely. Delta, theta, alpha, beta. Like having sliders for each one.
And just for context, those are the kinds of signals we measure with EEG, electroencephalography.
Okay.
They generally map to different states, right? Like the source mentioned, delta for deep sleep, beta for active thinking.
Exactly. You got it. So
Yep.
our mission here is basically to unpack what that video showed,
Mm.
look at the generator's features, how it seems to work based on the demo, and pull out some, surprising details.
It's like that point about bandwidth and amplitude.
Yes. Exactly like that. We want to kind of extract the key insights from that specific demo for you, the listener.
Okay, sounds good. So the core thing it showed was control over the whole spectrum, wasn't it?
Yeah, you could set parameters for each band individually. Delta, theta, alpha, beta,
Mm-hmm.
see them alone, or all meshed together.
Right, setting the amplitude, the bandwidth.
And the bandwidth, yeah, that was crucial. Oh, and the video mentioned the default window size was 5, I think.
Right, 5 units, whatever those units were in their system. But yeah, the parameters were key.
And that brings us to that really interesting bit you mentioned about changing the bandwidth.
Mm-hmm. What happened when you did that in the demo?
Well, the source pointed out that as you make the bandwidth wider for a signal,
Yeah,
the amplitude actually goes down.
right. Which can feel a bit backwards at first glance, can't it?
Totally. You'd think wider range,
Yeah.
bigger signal peak, but no.
But the explanation in the video made sense. It's about keeping the total energy in that frequency band the same.
Okay, explain that a bit more.
Well, think of it like, okay, imagine you have a fixed amount of water, that's your signal energy. If you push it through a really narrow hose,
Right.
it comes out with high pressure, right? High amplitude.
Okay, yeah.
But if you pour that same amount of water through a wide opening,
The pressure's lower.
exactly, lower amplitude.
Yeah.
So wider bandwidth means the energy is spread out more, so the peak intensity, the amplitude has to drop. The demo showed it happening.
That's a great way to put it. So it's a fundamental signal thing they demonstrated.
Precisely. It showed that principle in action.
The video also kind of dropped a couple of other tech details. Something about using Levy functions.
Yeah. Levy functions, they're sometimes used in modeling complex, kind of jumpy, random processes, not just smooth noise. So using them suggests, maybe a more sophisticated model underneath.
More than just basic randomness.
Potentially, yeah. And they also mentioned an API being available.
Right. What does that usually mean?
Well, an API, application programming interface, basically means they built it so other software could potentially talk to this generator.
So you could maybe plug it into
That, by the way, was the LabVIEW functions, but never mind.
The other research tools or something.
Could be. Or build something new on top of it. It opens doors.
Interesting. Oh, and one last detail, they called the beta band the gold standard at one point in the interface description.
Yeah. That likely just reflects how often beta waves are, focused on in certain types of brain activity research or applications. Kind of a nod to common practice,
Makes sense.
a common point of interest.
So let's try and wrap this up for everyone listening. We looked at this specific tool, this synthetic EEG generator from the video.
Yeah, focused on how it lets you control individual bands, tweak amplitude, tweak bandwidth.
Right. And saw that neat relationship where widening the bandwidth lowers the amplitude to keep energy constant.
That core signal processing insight.
So thinking about this specific simulation tool, what does it really tell you about, I guess, the complexity of real brain signals, even just trying to build these components piece by piece?
Well, yeah, that leads to the interesting thought, doesn't it? If you have a tool like this that lets you isolate and play God with these different brainwave ingredients, adjusting their spread, their intensity, what does that suggest about how all these different signals might actually blend and interact in a living, thinking brain? Or, what are the bigger implications of us getting better at synthetically creating these complex biological signals?
Definitely something to think about.
There's obviously some noise generation to it. Can you quickly review this thing that you see on the screen? You can be highly critical as well, and funny if you like.
All right. Looking at the interactive EEG brainwave simulator page, it seems like a pretty informative tool. The layout is clear, with the brainwave controls on the left and the power spectrum and waveform graphs on the right. The sliders make it easy to see the impact of different brainwave frequencies. However, maybe some more detailed explanations of what each brainwave frequency means, in practical terms, could be helpful for beginners. Also, the connection between the power spectrum and the waveform might be clearer, with some direct linking or visual cues. Overall, it's a good starting point, but could benefit from a bit more user guidance and explanation.
Okay, we actually have more explanation at the bottom of the page. So we have an explanation of what is EEG, brain wave deep dive, indicating what each brainwave frequency band is, and applications and limitations. So that should be complete, is it?
Ah, I see now. Having those explanations at the bottom definitely provides more context. The What is EEG, Brainwave Deep Dive, and Applications and Limitations sections add valuable information to help users understand the simulator better. That does provide a more complete overview of the content. It seems like it's a comprehensive resource then.
Okay, that's fine. Moving on to the technical side of things. What did you actually say about what do you think of the time domain chart? How does it look to you?
The time domain chart, the simulated EEG waveform, looks like it's accurately representing the combined brainwave frequencies. It shows the overall wave pattern that results from the mixture of the delta, theta, alpha, and beta waves, and it seems to change dynamically when you adjust the sliders. It appears to be a clear visualization of the combined waveform in the time domain, reflecting the changes in frequency and amplitude.
Can you be critical about it? What's missing? It doesn't look very realistic. Can you comment about potentially adding noise into the mix as another control and potentially making the window size larger? What do you think?
You're right, the simulated waveform does look quite smooth, perhaps overly simplified compared to real EEG signals, which usually have more noise and variability. Adding a control for noise levels would make the simulation more realistic and provide a better understanding of real-world data. Also, increasing the window size for the time domain waveform could allow for a longer view of the signal, which might be helpful for observing more complex patterns over a longer period. These enhancements would definitely improve the educational value of the simulator.
Okay, so I'll try editing this canvas in Gemini, but we also have it running locally as well, so we can potentially try using other models as well.
Okay, trying other models or editing in Gemini could provide different perspectives or ways to implement those suggestions. It might offer various approaches to enhance the realism and functionality of the simulator, like
Okay,
integrating noise
what's the
controls.
agent? What's the agent currently doing? Can you summarize that?
The agent is currently updating the simulator to incorporate your feedback. It's adding a noise level slider to the main control panel and increasing the window size for the time domain waveform chart. This will allow for a more realistic and extended view of the simulated brainwave signals.
Okay, it's actually did a pretty decent job. So this is Gemini 2.5 Pro. Thank you very much.
You're welcome. I'm glad it was helpful. The addition of the noise control and the larger window size should definitely make the simulator more realistic and insightful for users.
Okay, can you comment on the default settings when we loading the page? Looking at like EEG literature, what do you think of those settings currently?
The default settings for the brainwave controls like delta, theta, alpha, and beta power seem to represent a mix of different brain states, but they might not correspond to one specific state. Typically, EEG literature shows different patterns predominant in states like deep sleep, relaxation, or active thinking. Adjusting the default settings to reflect a more typical brainwave profile for a known state, like emphasizing alpha waves for relaxation, could make the simulator more relatable to standard findings.
Okay, so what are you suggesting? Are you suggesting a drop-down menu that will have different presets for the EEG, and which one would you choose by default? And if you had a drop-down like that, what items would you have in it?
Yes, adding a drop-down menu with presets would be a great idea. For a default, a relaxed alertness preset, emphasizing alpha waves, would be a good starting point, as it represents a common brain state for many people. Other presets could include deep sleep with predominant delta waves, meditation or drowsiness with theta waves, and focused concentration with beta waves. These would allow users to explore different brainwave patterns associated with various cognitive states. Sure, here is a technical brief for the developer. Implement a drop-down menu in the Signal Control section. This menu should provide presets for different brainwave states. The default selection should be Relaxed Alertness, which emphasizes alpha waves. Include other presets such as Deep Sleep, emphasizing delta waves, Meditation/drowsiness, emphasizing theta waves, and Focused Concentration, emphasizing beta waves. When a user selects a preset from the menu, update the corresponding slider values in the Signal Control section to reflect the typical brainwave profile for that state. Ensure that the power spectrum and simulated EEG waveform charts update dynamically to visualize the new brainwave patterns. This feature should enhance the user's understanding of different brain states, as described in EEG literature. The developer agent is currently working on incorporating a drop-down menu into the interactive EEG brainwave simulator. Their process involves designing the presets for different brain states like relaxed alertness, deep sleep, meditation/drowsiness, and focused concentration, and then implementing the drop-down menu in the code. They are setting up the JavaScript to update the sliders and charts dynamically based on the preset selected, with relaxed alertness as the default values. The response provided details the key changes and how the new feature will enhance the simulator's interactivity and educational value. The developer is currently implementing a drop-down menu for brain state presets, designing the presets with specific brainwave amplitudes, and setting up the JavaScript to update the sliders and charts based on the selected preset. They are also planning the integration with the existing code. Regarding the time series charts, the simulated EEG waveform might appear weird because it's representing a combination of different brainwave frequencies and potentially noise, which can result in complex and seemingly regular patterns. Without seeing the specific time series data for each preset, it's hard to give a precise critique. But ensuring the simulated waveforms align accurately with the known characteristics of each brainwave frequency is crucial for the accuracy of the simulator. Perhaps adjusting the amplitude and frequency modulation for each preset and adding more nuanced noise characteristics could improve the realism of the waveforms. Sure. Oh, sure. The time series waveform for relaxed alertness shows a mix of alpha and beta waves. You can see the more regular, smoother patterns from alpha waves, indicating a relaxed state, combined with some faster waves from beta wave activity, which suggests a level of alertness and focus. The combined waveform looks like a blend of these two patterns, which is consistent with being relaxed but still attentive. Yes, based on the description of relaxed alertness and the combination of alpha and beta waves, the time series waveform appears to be correctly simulated. It shows a pattern that aligns with both relaxation and some alertness. For Under focus concentration, the frequency spectrum typically shows a significant peak in the beta wave range, indicating active thinking and mental engagement. There might be also some alpha wave activity, suggesting a state of focused attention without excessive arousal. The time series waveform would likely appear more complex, with faster fluctuations due to the prominent beta waves, reflecting the heightened mental activity. Yes, changing the noise level will definitely affect the frequency spectrum displayed in the chart. Noise in this context represents random, unwanted signals that can obscure the underlying brainwave patterns. When the noise level increases, it adds a broader range of frequencies to the spectrum, making it harder to distinguish the specific frequencies associated with the actual brainwave activity. The peaks representing the delta, theta, alpha, and beta waves might become less clear or more distorted as the noise adds background signals across the frequency spectrum. In the time series waveform, increased noise would make the signal appear more erratic and less distinct, making it harder to see the underlying patterns of the specific brainwaves. All right, sharing it with the developer would be a good idea. They can provide feedback on the accuracy of the simulations and any potential improvements. It's always helpful to get expert input to ensure the simulator is working correctly. The developer agent is acknowledging your feedback about the noise effect on the frequency spectrum. Initially, the simulator was likely displaying an idealized spectrum based on clean signals, separate from the noisy time domain waveform. The agent's plan is to update the code so that the power spectrum is calculated directly from the noisy time domain data. This approach will create a more realistic representation, showing how noise affects the frequency components in a way that mirrors real EEG analysis. The response from the developer indicates they understand your point and are implementing the change to make the simulator more scientifically accurate and educational. You're right. From a scientific standpoint, the updated simulation is more accurate and realistic because it reflects how noise impacts real EEG data. While it might be less clear visually at first, it provides a more truthful representation of the challenges in analyzing real brainwave signals. So, yes, it's better in terms of scientific accuracy and educational value. Yes, that's exactly what the updated simulator demonstrates. The time domain waveform becomes increasingly chaotic and difficult to interpret with high noise levels. However, the frequency domain chart, even with noise, still shows the underlying frequency components, albeit with a raised noise floor and potentially less prominent peaks. This accurately represents the challenge of signal detection in real-world EEG analysis, where noise is always present. You're correct. The typical frequency range for EEG analysis usually goes from around 0 to 30 Hz. The current display only showing up to around 11.7 Hz might be a limitation of the simulator's current settings or visualization. The developer should extend the frequency range to provide a more complete and accurate view of the brainwave spectrum. Yes, adding a toggle control for the individual brainwave components would be a great enhancement. The developer could modify the chart's rendering logic to include options to show or hide each brainwave frequency band separately. This would involve updating the visualization code to conditionally display the data for delta, theta, alpha, and beta waves, possibly using checkboxes or a drop-down menu in the signal controls. This would make the simulator more interactive and educational, allowing users to examine the contribution of each frequency band more clearly. To enhance the simulator further, I would suggest a few key changes. Firstly, improving the realism of the noise simulation to better reflect real-world EEG artifacts would be beneficial. Secondly, incorporating more brain states beyond focused concentration, such as relaxation, sleep, or meditation, would increase the simulator's versatility. Additionally, allowing users to input custom parameters for brainwave frequencies and amplitudes would provide more flexibility in exploring different scenarios. Finally, a more intuitive and user-friendly interface could make the simulator more accessible to a broader audience. The agent is currently updating the simulator to incorporate your feedback. It's extending the frequency range to 30 Hz, adding toggle controls for individual brainwave components, and likely also improving the realism of the noise simulation and user interface. The error message you showed indicates a type error, cannot read the properties of null, reading add eventlessness. This suggests that the code is trying to add an event listener to an element that is currently null or doesn't exist in the document yet. It might be happening because the code is trying to access a specific element before that element has been fully loaded or created in the web page. The agent is focusing on identifying the root cause of the type error. It's reviewing the code to determine which element is being accessed prematurely and causing the null error. The agent is likely adding checks to ensure that all necessary elements, especially the slider elements, are fully loaded and available in the document object model, DOM, before attempting to attach event listeners to them. This will prevent the error by ensuring that the code doesn't try to interact with elements that haven't been created yet. The agent is now refactoring the code to fix the event listener issue. It's specifically using the query selector instead of document by element ID within the loop to ensure that elements are correctly referenced even if they are dynamically loaded. This should resolve the null error and make the event listeners work correctly. Looks like the code is trying to listen for events from an element that hadn't even shown up to the party yet. It was like trying to have a conversation with a ghost in the machine. Hopefully, the fix will get everything on the same page now. The code is around 200 lines long, which is quite manageable for a simulator like this. As for editing time, it would depend on the specific changes required. Simple tweaks, like adjusting frequencies or fixing small errors, might take a few minutes. More complex additions, like adding new brain states or significantly overhauling the visualization, could take longer, perhaps hours. Overall, the code appears manageable for
Yeah, we lost our prompt engineer. And so we have all these tools already deployed, making a better version of the EEG signal generator. We're adding audio description for this joint time frequency scattering, for seizure detection. We added a very long, not a very long, like about 20 minutes of audio to this EEG seizure detection project, because there's quite a lot to it. We have the EEG to music, go check it out. Some blogs that hopefully about the event related potentials in this case, that hopefully eventually will turn into interactive, more useful web applications on the site. So everything we do is available on this website, BioniChaos.com. Go check it out and let me know what you think. Okay, now that it starts making errors, I'll actually go back to this version. Might have to revert a few versions back. Let's try. We'll try calling our prompt engineer again. See if they pick up the phone. Yeah, let's have another version of this thing. So I have the copy, and then we'll have the new version as well. Why is it shorter? It should not be shorter, should it? Okay. Okay, can hide. Oop. Edit eye blinks, muscle. It's actually really nice. I still have to be testing it. I don't know what this spectrum. We need a prompt engineer. We really need a prompt engineer. We can't get hold of the prompt engineer. Mueller. Okay, we have a prompt engineer. Hello. We're live streaming. Hopefully, you can address the viewers directly. Can you briefly explain what you see on the screen?
The screen displays an EEG signal simulator. It shows different brainwave frequencies like delta, theta, alpha, and beta, and also shows simulated artifacts like muscle activity and eye blinks. You can adjust the levels of these waves and artifacts to see how they affect the signal display. I see. One, one improvement could be to add more interactive features, such as allowing users to click on the graphs to see more detailed information about specific frequencies. Also, incorporating explanations for how each artifact impacts the signal could be beneficial. Yes, this version appears to be more interactive and informative. The clickable graph and the additional information about brainwaves make it more engaging for understanding the data. It also includes a noise level slider, which provides a more realistic simulation. The newer version is better because it provides more interactive features, like the clickable graph that shows detailed information, and it includes a noise level slider, which makes the simulation more realistic. It also provides clear explanations of the brainwaves, which enhances the user's understanding. Yes, you're right. The frequency domain displayed indeed goes from 0 to 15 Hz, And there are many decimal points on the frequency axis, which might not be necessary for a user understanding. Adjusting the frequency range and reducing the number of decimal points could improve the clarity of the display. The developer agent is reviewing the frequency issues with the power spectrum chart. They're noting that the frequency range should extend to 40 Hz as per the code, but the chart currently shows only to 15 Hz. They are also looking into the excessive decimal points on the frequency axis and plan to adjust the scaling to improve clarity. They have reformatted the data structures and updated the axis configuration to ensure the frequency range is displayed correctly up to 40 Hz. They have also adjusted the labels to reduce the number of decimal points, improving the clarity of the power spectrum chart. The interactive EEG brainwave simulator, which is likely the index_copy.html version, seems superior because of its interactive features, clear graphs, and informative details compared to the advanced EEG signal simulator. Yes, that's a great idea. You can enhance the advanced EEG signal simulator by incorporating the interactive features and improved clarity from the interactive EEG brainwave simulator. You can maintain the advanced options while making them hideable to provide a cleaner and more user-friendly experience. You can add additional sliders or input fields for each brainwave frequency to control their specific bandwidth or range, similar to the existing sliders for frequency and amplitude. This would allow users to customize the frequency characteristics of each brainwave, just like the table shows. The table displays key information about primary brainwave frequencies, including their typical frequency ranges, typical amplitudes, and associated states and functions. The developer can use this information to enhance the customized advanced options, allowing users to adjust the frequency ranges and amplitudes of each brainwave according to these standard values. This will make the simulator more accurate and informative. Got it. You want the developer to add a single input field for bandwidth in the fine-tune wave section. This field should allow users to specify a plus-minus range for the frequency of each brainwave, making it easier to customize the waveforms. Okay, here's a brief for the developer. Please enhance the customized advanced options to allow users to adjust the frequency and amplitude for each brainwave type. The default values for frequency and amplitude should be based on the provided table. Delta waves with a frequency of 0.5 to 4 Hz and amplitude of 20 to 200 microvolts. Theta waves with a frequency of 4 to 8 Hz and amplitude of 20 to 100 microvolts. Alpha waves with a frequency of 8 to 13 Hz and amplitude of 20 to 60 microvolts, and beta waves with a frequency of 13 to 30 Hz and amplitude of 2 to 20 microvolts. Ensure these values are correctly reflected in the user interface and that the user can adjust them accordingly. The developer is focusing on two key areas: updating the input ranges for the frequency sliders and integrating the microvolt input display. They've already modified the frequency sliders to reflect the correct ranges from the provided data. Now, they're working on mapping the amplitude sliders' percentage-based values to the appropriate microvolt ranges. The goal is to provide a clear and accurate display of the input values in microvolts while maintaining the existing simulation logic. They are also adding tooltips to guide users. The overall aim is to make the advanced options more intuitive and informative. They are implementing the adjustments to the advanced parameter controls, specifically incorporating the accurate frequency ranges and amplitude microvolt values for each brainwave type. They are also refining the user interface to display the microvolt values clearly and ensure a seamless integration with the existing simulation logic. Okay, the developer should keep the fine-tune wave section as is, but make a couple of visual adjustments. First, arrange the delta and percentage slider elements on a single line for a cleaner layout. Second, when the user clicks the Customize button, add a bandwidth field for each brainwave type, delta, theta, alpha, beta, and set their default values. All other functionalities should remain the same as before. The developer is focusing on enhancing the visual appeal of the fine-tune wave section. They're working on redesigning the layout using a grid structure to arrange the wave controls horizontally. They're also considering adding a bandwidth field that would appear when the Customize button is clicked, aiming for a cleaner and more organized presentation.
They've integrated the bandwidth control into a new advanced customization section. This allows them to adjust the bandwidth of the waves, making the simulated signals more realistic. They've also updated the underlying signal generation logic to incorporate these new bandwidth values.
The key changes are a cleaner layout for the fine-tune wave section, where controls are now arranged horizontally, and the addition of a bandwidth customization feature in the advanced customization section. This allows for more realistic signal simulation and a better user experience. The main focus was on improving the visual layout and adding the bandwidth control. The core functionality for simulating brainwaves remains the same, but the simulator is now more realistic and user-friendly. Sure, here's a revised brief. In the fine-tune wave section, maintain the existing layout where frequency and amplitude sliders are displayed horizontally. Upon clicking the Customize button, add a new bandwidth control alongside the existing frequency and amplitude sliders. Ensure that the new bandwidth control has appropriate default values for each brainwave type. The overall layout should remain clean and intuitive. The agent is currently focused on implementing the bandwidth control within the fine-tune wave section. They've designed the UI to include a new bandwidth input field that appears when the Customize button is active.
They've also updated the underlying JavaScript functions to handle the bandwidth values and ensure they are correctly reflected in the signal generation calculations, particularly within the ideal spectrum function. The goal is to create a seamless integration for the bandwidth control.
Okay, we lost our prompt engineer again. Okay, Claude was actually Claude Sonnet 4 was actually able to do what we asked for. I think. What? It's not actually. Hey, can we double check if the bandwidth actually changing the signal? It doesn't seem to change the frequency domain. The width of that remains the same. Wouldn't let me
You're
finish.
absolutely right. The bandwidth parameter is defined but not actually being used in the signal generation or spectrum calculation. Let me fix this by updating the ideal spectrum function to use the bandwidth parameter and modify the signal generation to...
Okay, I can do it quietly because I don't like the... let's see, what's Gemini up to? Okay, it's also added bandwidth. Okay, so if we have an amplitude, same kind of problem. Yep, same problem. I think just refreshing the thing. Okay, Gemini 2.5 Pro. Well, it was able to do a lot of things, but once we trying to modify something, it's not doing great anymore. Claude broke something as well, yeah. Ah, no, that's fine. Yeah, so we have delta there. Delta bandwidth. Okay, now it's actually working. So that's nice. Okay, we have higher delta in sleep as expected. Customize bandwidth. Yep. Okay, that works. Okay, let's use for all quick. Start a new chat. Can you quickly explain why in customize, so when we fine-tuning waveforms, in customize the amplitude percentage?
In the Customize mode for fine-tuning waveforms, users are provided with more granular controls to adjust the frequency, bandwidth, and amplitude.
Yeah, that's fine, but in that control, in that section, we're only able to change the frequency and bandwidth, but the amplitude is grayed out. I understand that you can change it in the regular sliders, but we want to be able to change them in both places, don't we?
To allow amplitude adjustments in both the sliders and the fine-tuning inputs, we need to enable the amplitude input fields in the fine-tuning section and ensure.
Okay, you can do it quietly. Let's see if it's actually on the nose. Okay, it's actually working. Okay, real quick change in the spectrum overlays. Can we have all the bands ticked by default, so they're displayed on the spectrum overlay?
Index.html. Update the spectrum visibility object to have all.
I don't like this voice. I don't know if you can change the voice or not. Okay, that's nice. Now the signal spectrum one, should it be a combination of all the energy, all the bands combined? Is it? Or can you explain that bit?
The signal spectrum, power spectrum, displayed on the chart labeled power spectrum, frequency domain, is indeed a combination of all the energy from the selected brainwave bands, delta, theta, alpha, beta, and any artifact.
Okay, and is it correctly showing the correct thing at the moment or not? I'll give you a clue. It's not.
Yes, the current implementation is correctly showing the combined spectrum of all the selected bands, delta, theta, alpha, beta, and artifact.
Okay, this is interesting. Let's do a Gemini 2.5 Pro and redo the last response. See what it says. Because it's incorrect. Okay. Let's do Sonnet 4. Okay, can you double check the code? The signal spectrum doesn't seem, well, at least when we change the parameters, when we fine-tuning the waves, it doesn't seem to be a combination of everything. It seems to be only covering the noise. It seems to be only the noise or something.
You're absolutely right. I found the issue. The problem is in the generate noisy signal function. It's only processing brainwave bands that have parameters already set in waveforms, but when the page loads, waveforms is empty until a preset is applied. Index.html. Fix the signal generation to ensure all brainwave bands are always included in the spectrum calculation, and
Okay, so I did find a problem. This is Claude Sonnet 4. This video is brought to you by Claude Sonnet 4. Um, can you double check the code again? I think there's a problem. The signal spectrum is not covering all the individual bands. I think it's only covering the noise. While it's generating, you know what to do. Like, subscribe, check the website. Everything we do is available on this site. So go check it out. Check it out. Don't know what takes forever.
It's puzzling that the signal spectrum isn't reflecting the brainwave bands correctly. The logic for initializing waveforms and applying presets seems sound, where preset amplitudes should overwrite any initial zero values. Also, the ideal spectrum overlays, appearing correctly, it suggests waveforms holds the correct non-zero amplitudes when update charts is called. The most likely reason for brainwave components to be missing from the signal spectrum, the solid blue line, while artifacts are present is if their amplitudes, waveforms, key.amp, are effectively zero when generate noisy signal is called. Let's try two things. A slight adjustment to the initialization sequence to ensure waveforms is fresh before apply preset populates it. This is more.
Okay, we'll have to continue this next time. And eventually it will become available on the website. So go check it out. Stay tuned. Like, subscribe. You know what to do. Any nasty comments are welcome to. Bye.